Hi friends, welcome to my channel. Let's have a look at a classic problem. Problem 124, binary tree maximum pass sum. In this video, we are going to share a solution based on recursion. First, I'll read through the statement to digest the requirement, and then we do the analysis and share the code, and finally we simplify a little bit the code. First, let's look at the statement. So we are given a binary tree, and we want to compute the maximum pass sum of any non-empty path. So here, the main point to be noticed is that the path does not need to pass through the root. So let's look at the two examples given here. The first example is sort of simpler. The reason is that all the node values in this tree is positive. So we want to include as many nodes as possible. So in this case, we can consider the 3 nodes path. So 2, 1, 3. The path sum is 6. So the maximum path sum for this tree is 6. In example 1, we notice that the root of the whole tree has a negative value, right? So here we can examine 2 paths for example or for comparison. So one path passing through the root at level 0 is 9, negative 10, 20, or go to 15 because 15 is larger. So this is one path. So we can consider another path passing through the node at level 1 as 20. So we get 15, 20, and 7. So the first one, actually 9, negative 10, 20, and 15, has a smaller path sum compared with the path passing through 15, 20, and 7. So actually for this problem, the maximum path sum is corresponding to this path, 15, 20, 7. That is 42. So before we look at the analysis, let's also look at the constraints. And first, the number of nodes in the tree is in the range 1 and 3 times 10 to the power 4. So these two numbers are the two ends of the closed interval. So here 1 actually tells us this tree is not null, and the other end tells us the problem size. So this is the first constraint. Another constraint or assumption is that the values of the nodes are bounded in between negative 1000 and positive 1000. So in particular, this assumption or constraint tells us that the node values can be negative. So this actually is important information. With that said, let's look at the analysis. So here we are going to use recursion. So actually recursion is natural for this problem because the data structure behind is binary tree. And binary tree can be defined recursively, right? So we want to emphasize again, so here a path does not need to pass through the root. So with that said, let's look at the main idea and the procedure. So for each node, we are going to compute 2 pieces of information. So I'm going to call them L and R. So the interpretations of L and R are the following. So L will be the maximum path sum starting from the node and next going to the left subtree downwards. And R is the maximum path sum starting from the node and next going to the right subtree downwards. So I want to also mention a note. So here we only care about go to left or right from the current node to its child. But we do not care about which direction to go from child and onwards or downwards. So with that said, so we can actually get the maximum path sum passing through the current node and with current node at the highest level. Let's call this the maximum sum. So we examine the 2 pieces of information for the left subtree and right subtree. So I'm going to call them LL and LR and RL and RR. So this interpretation are very straightforward over both or self-explanatory. So I'm going to assume little m will be the smaller of the or the larger of the two pieces of information for the left subtree, and the capital M corresponding to the right subtree. And then we're going to compute the maximum sum passing through the current node, and the current node being the highest level. For example, this root 15, 20, and 7. So the 20 is the highest level, level 1. So these two nodes have level 2. So here the details are the following. So if little m is not positive, then we consider two cases. First, if capital M is also not positive, then the maximum sum will be the node value itself, because we don't want to go to left or right because they correspond to negative values. If the capital M is positive, then we can go to the right from the current node. So the maximum sum will be node value plus capital M. So this is the case for little m is not positive. Then we consider the case little m is positive. So in this case, for sure, we can move to the left. We are going to check if we can move also to the right according to the sign of capital M. First, if capital M is not positive, then we can go to the left only, right? So the maximum sum will be little m plus node value. Otherwise, if the capital M is positive, then we can extend our route, our path from the current node to both left and right, downwards. So the maximum sum will be the sum of the three pieces of information, little m, node value, and capital M. So that's the full detail. So our plan will be the following. So we are going to write the code following the above idea verbosely for a detailed understanding. And then we simplify a little bit. So actually the code can be further simplified, but if we write in this fashion in a verbose way, so it helps to digest the idea. So before we write the code, I guess a walkthrough might be helpful. So here I'm going to use example 2, because example 1 is sort of simpler. So for example 2, I'm going to first look at the leaf nodes, because leaf node, we can easily get the L, R, and maximum sum corresponding to them. So for example, for the node none, the L is none, R is none, and the maximum path sum passing through it and with it as the highest level is none. So similarly for the node 15 and node 7. All these three nodes are leaf nodes in this tree. So next we're going to compute the corresponding information for 20 for this tree. So for 20 we can actually get L is 20 plus the max of the two information for the tree 15. That is 15, right? So we get L is 35. Similarly, R is 20 plus the max of the two pieces of information for the right subtree 7. That is 7. So we get 27. And the maximum sum is the max of 15, 15 corresponding to this tree plus 20 plus the max of the two pieces of information corresponding to tree 7. So that is 7. So overall we have 42. So next we can look at the two pieces of information for the root at level 0, that is negative 10. So for this we get L equals negative 10 plus the max of the two pieces of information for the left subtree, that is none. So we get negative 10 plus none, that is negative 1. So similarly we compute R is negative 10 plus max of the two pieces of information for the root or the right subtree 20, that is 35 and 27. So overall we get 25. So the maximum sum of the path passing through the root and with the root at the highest level is nothing but the max of the left subtree, that is none, plus the root value itself, plus the max of the two pieces of information for the right subtree, that is max of 35 and 27 for this tree 20. So overall we have a result 34. So if we compare all these max sums, so we're going to get 42 being the max. So this corresponds to the paths 15, 20, and 7. So that's the output 42 for example 2. So with that done, so I guess we explained the idea and use the idea to give a walkthrough for example 2. So now let's look at the code. I feel that the code now is very straightforward. So for this, first I'm going to introduce an attribute. Let's call it answer. So because we are going to compute the max, so I'm going to use here negative infinity, because we are going to take max about the intermediate max path sum. So this is one preparation. So next we are going to write a hyperfunction. So hyperfunction. So we are going to accept a node, and then for this node we are going to compute two pieces of information, the L and R above. So first, let's consider a case that is a base case or a stop condition. If not node, we are going to return 0, 0. So this is natural. We have nothing, right? So we return 0, 0. So next, so we're going to first gather the information for left subtree and right subtree. So here is a recursion function call or self call. It's node left. So we're going to get the information for the right subtree, that is node right. So with these two sets of information, actually we can get the information for the node itself. First, I'm going to call this little m and capital M being the max of the left subtree information, and the max the right subtree information. So with that done, so let's follow the above analysis to give our both coding, and then we simplify. So first, I'm going to consider the case is little m is not positive. So in this case, we are not going to go to left, right, because its contribution is not positive. And then we're going to check if we can go to right. So we are going to check if the capital M is not positive, then we do not go to the right. So in this case, the maximum sum will be a root value or the node value itself. So in this case, so we're going to update the self answer to be self the max of self answer and the node value. This is one case. Another case is that the capital M is positive. So in this case, we can go to the right subtree from the current node. So the max will be self answer, and we can go to right, right? So we're going to plus this m. So this is one case. Next, we're going to consider the case the little m is positive. Then in this case, we can go to left subtree from the current node. Then we consider if we can go to the right subtree also. So first, let's consider the case capital M is not positive. In this case, we go to left only, but not go to right. So we're going to have self answer equals max self answer and node value plus little m, because we can go to next left. Otherwise, the capital M is also positive. So in this case, we can go both left and right. So we are going to have little m plus node value plus capital M. So that's the update for the global maximum path sum. So now, in order to get the information of LR for the current node, so we are going to return. So first, we are going to have this part, root value, because this is always included. So we are going to check if we are going to go to left. So we are going to consider this plus little m. So this, if little m is positive, then the maximum of this one will be this one, right? So similarly, we can get the right information. First, the root value should be included, and then we can check if we can go to right. If we can go to right, means capital M is positive, then this will be the ladder. So that's the hyperfunction. So here, let me check. I use node here, node. So let me change to node. Right, so now we are ready to do the function call. So next we're going to call this function, but we start from the root of the original binary tree in the argument. So once we call this function, so we can understand this function as a worker. So it's going to update the answer attribute. And then what we're going to return is nothing but self answer, the final state. So with that done, so I guess this forms a full solution for this problem. So now what we're going to do is to do some tests first. Yeah, it passes the simpler example. Now let's look at generic case. Yeah, it passes all the cases. So with that done, actually this code can be modified in a number of ways to make it shorter or more compact. Let me copy the whole code and put it here. But I guess this version or this format is easier to understand for us. So now let's change this one to be v1. So here, actually, if we understand logic, so we can change this one, right? Change this one to be like this. So self answer, we just update once. So we're going to have, so we want to check if we can go to left or right. So first we need to have the previous state, right? And then what we're going to do is that we can do this. So this, it will help us to check if we can go to left, right? If the max is 0, it means that we do not go to left, or we do not need to go to left. And then we put node value, and then plus max of capital M and 0. This max of capital M and 0 checks if we can go to right, or if it's necessary to go to right, right? So this actually simplifies the code, and this function actually writes a lot of logic inside. So this max considers the previous state and the current maximum pass sum passing through this node, and using this node as the highest level. So with that said, or with that modification, let's do a check again. It passes the test case, now generic case. Yeah, it passes all the generic cases. So I guess with that said, and that's about it for this problem or for this video. For sure, this code can be even simplified further, but I would prefer to use the first format to digest the problem and the logic. With that said, that's it. Thank you.